DD Solar here. Thanks for tuning in. I have a number of these 18 volt Ryobi power tool batteries. This one is a generic, but they work about the same. Over the past few weeks, I've amassed quite a few different Ryobi power tool batteries and also the chargers, and some of them aren't working. An example would be this one here. This one is burnt out, and I cut off the power brick because I think that's the reason for the problem. What I would like to do is start modifying these power tool battery chargers, but I didn't really want to tear up a working charger. I have several of them. What I did is I went on eBay and I bought some equipment that wasn't working, and some of the equipment was Ryobi power tool battery chargers. Now here's the power brick. This doesn't work. I've already verified it. There's no voltage coming out, and so it must have burned out or something. That's my guess. Or it could have been dropped. It has some scratches on it. Who knows? It could have been dropped. What I would like to do is see if I can run this type of charger off of a solar panel. In order to do that, the first thing I would do is look at the power brick itself, and you can see it says right on there, output is 18 volts. Of course, this one here isn't working, and I wasn't able to get a measurement off of it because it's completely dead. I was able to get the voltage measurement from this power brick, which is from another charger that is working. As I suspected, 18 volts is not the truth. It's actually putting out about 21.5 volts. So this type of charger apparently needs 21.5 volts to function, which would make sense because power tool batteries would be 21 volts when fully charged if it's a 5-cell lithium-ion design. What I want to do is take a solar panel that has a variable voltage and charge my power tool batteries safely using the OEM Ryobi charger, except it would be modified. In order to do that, the solar panel is a variable voltage source, and we need 21.5 volts. So I would need 21.5 volts going into the charger at a minimum, and I do think it would work with less than that, and I may actually deliberately put in less than 21.5 volts, and I'll get into that in just a minute. So the solar panel that I'm going to be using is a 100 watt, and it's a monocrystalline panel, and it puts out about, in open circuit, it could put out 18 to 19 volts. 18 to maybe 19 volts. But when it's under load, it really sags down, and all the panels from this batch that I purchased, they seem to have incredibly low output, and they can be down to around 15 volts in some conditions when they're loaded. So I'm going to say 15 to 18 volts, and it could be as high as 19 volts. Now the power tool battery is going to require at least 21 volts to get a decent charge into it. But if I don't want to charge the power tool battery all the way, I could say 20 volts or 20.5 volts. However, the solar panel would not be able to fully charge the power tool battery because its voltage under load is going to be much lower than the power tool battery would want. In order to get good voltage into the charger, I'm going to have to use some kind of electronic circuit. I cannot just plug a solar panel straight in. That is not to say I won't try plugging a solar panel straight in, because I like doing that. So in order to get a good voltage into the charger from a solar panel, which is a variable source, I'm going to need either a boost converter or a buck boost converter. And there are potential applications for both of these circuits. There is one big problem though with a boost converter. So a boost converter can only raise the voltage up. So it will easily hit 21.5 volts. That's not a problem. But there's a security problem with this type of design, and the reason that is the boost converter can only boost. And if it's a constant current, constant voltage boost converter, which is of course what I'm going to use, I'm not going to use anything else because I want to limit the current. There's a problem. If you go into constant current mode, the boost converter cannot limit anything below its input. So if you're getting 18 volts into the boost converter, when it tries to limit the current, if it falls down to 18 volts, it can't go any lower. And at that point, the output current will be whatever the input can supply. Therefore, it becomes a bit dangerous, and you could have an overcurrent condition and burn something up. Now, a buck boost converter both lifts and lowers the voltage, and so it's much more flexible, and it's able to limit the current down to a low voltage if necessary. That's because it has a buck circuit in it. A buck converter by itself isn't going to work because my solar panels don't even produce enough voltage for the solar panel in the first place. So I'm forced to use either a boost or a buck boost converter, and those are my choices. If I had a higher voltage solar panel, of course I would use the buck converter with constant current, constant voltage. But it looks like I'm going to be going with a buck boost converter because I don't like the feeling of knowing that a boost converter can't really protect from overcurrent when the voltage starts to fall too low. Imagine a power tool battery that was deeply discharged, and for whatever reason the voltage was high enough that it could cause an overcurrent condition. The boost converter would not be able to do anything about that. If it was down around 14 or 15 volts, it would just pass the solar panel right in and the current would go right in. It would have no way to limit the current. Let's say you have a 12 volts at 100 amp source. Let's just say it's a battery. It can put out 12 volts at 100 amps, and you put that into a boost converter and you boost it to 24 volts. But you only want 5 amps. So let's say you hook a load up to that. And it doesn't matter what it is. It could be a light bulb or anything. That would be about 60 watts. And actually it would be 120 watts. It doesn't really matter. So 120 watts. Now let's say for whatever reason you have a short circuit. So let's just pretend there's a short circuit right here. So all that power goes into the short circuit. Now this circuit could have a fuse or some kind of polyfuse or just any kind of protective device. Let's just assume it doesn't have that. When the short circuit takes place, the boost converter, being as it's a constant current, constant voltage boost converter, it's going to try to drop the voltage to keep the current at 5 amps and not allow it to exceed 5 amps. But the problem is it can't go any lower than 12 volts because it's only a boost converter, it's not a buck converter. So what happens is, if there's a short circuit, assuming there aren't any other protective devices or circuits designed to protect from overcurrent, this 12 volts at 100 amps is going to go right into the boost converter and right over to the short circuit, and it's going to blow up. It's going to explode. It's going to burn it out. And there's no way to protect from that other than a fuse or some kind of intelligent circuitry inside the boost converter. And a lot of boost converters do not have any intelligent circuitry like that. If this circuit was a buck converter, constant current, constant voltage, if there's a short circuit, what it ought to do, in order to keep the current from going over 5 amps, it should drop the voltage down, if necessary, to 0 volts. Now, if you drop your voltage down to 0 volts, you're okay. You have the ability to prevent damage. And so that's what would happen. Once the current started to go up over 5 amps, the current would exceed the limit, and instantly the buck converter, I'll just write buck converter, at 0 volts, it would drop its voltage to 0 volts and thereby prevent any damage. It would be able to control the current. It would probably still let 5 amps go through, but there would be no damage because it's only allowing 5 amps and the circuit can handle 5 amps, so even though it's a short circuit, it can handle it. Now a buck boost circuit is able to raise the voltage up or drop it down, regardless of the input, and a constant current, constant voltage buck boost converter is probably what I'm going to end up using in this application, which is modifying a Ryobi power tool battery charger. And this knowledge would be applicable to probably any power tool battery charger, but that's what I have. I have a Ryobi, so that's what I'm going to do. I'm going to modify that. So getting back to the charger itself, here's the one that has the failed power brick. I want to open this up and investigate to see what's inside and how to modify it so I can run it off of solar. This charger has these Torx head screws, and I found that this, I don't have the exact bit that would work, but I have this one here that's a triangle. That is not the correct bit. However, it just so happens to fit, and I'm not saying that's the right way to do it, but it fits pretty snug actually, and I'm not putting a lot of torque on these screws, so I don't think that's really a problem. One more screw. This power tool battery charger came from an auction site, and I don't know where it came from. Other than that, I don't know what happened to it or what it was used for. It is used, but it seems to be in half good condition, so I hope I'll be able to use it for this experiment. Let's open it up. Alright, there we go. See if I can get the camera to focus on that. The circuit board is coated with a conformal coating. That's why it's so reflective. And I have to be careful how I angle it because the light will reflect off of it. And there's some intelligence going on in here. You've got a chip there. This is the positive and negative of the battery. This right here is the communications, I believe, with the battery. So this is an extra connector. I believe that's what that is. And that's so it can communicate with the battery. You can see there's an extra contact here, and there's also one here. So the Ryobi batteries have a little bit of intelligence to them, and the charger communicates with it. Not a whole lot going on here. Here's the inputs for positive and negative for the charger to come in. There's where the cord was cut. There are actually two connections other than positive and negative, and I don't know off the top of my head what this one here does. It could be a thermocouple or some way to detect temperature in the battery, or it could be for some other purpose. I'm not too concerned about it. There's the contacts, and there is a fuse right there. It's like a ceramic fuse maybe. And yeah, there's a capacitor. I don't know what that little thing there is. It looks like a transistor, but I don't know what it does. You got your charging lights, plenty of white goop. That's the power input from the brick. There's not a whole lot on here. These chargers are built to be fairly cheap. I believe these are either diodes and or MOSFETs or switches. And so these would turn the circuit on and off. If it was charging the battery and it reached full, it would just turn it on or off. Now I don't know exactly what everything is on here, and I can't tell you whether these limit current or what they do. Obviously there's going to be some kind of overcurrent protection on here. It's an intelligent board. But everything here looks fine. There doesn't appear to be anything wrong with the circuit. And I'm pretty sure I'll be able to use this in my project and make it run off of a solar panel. So the question is, what do I need to do to make that happen? Well, for starters, I want to do some testing by attaching a 2.1mm jack to those input wires where the power brick used to be. Then I'll be able to plug things in and just try things out, see what's going on, see if anything happens. And because this was purchased in an unworking condition, you know, I'd hate to burn it up, but if I burn it up, it is what it is. I'm not risking any of my other tool chargers. I'm attempting to get some good footage of the circuit board. We need to identify the polarity. If this board was hooked up backwards, I'm quite sure it would burn up. If you look here, there's a charge negative. It's kind of hard to read. And there's a charge positive right here. They actually marked the board. I think that's really nice. I love it when they mark the board and you know what's on here and where it connects to. So obviously that would be positive and that's negative. So we would need to make sure and get the polarity correct while attaching the 2.1mm jack. I will connect this 2.1mm jack, and this side here is negative, this side here is positive. So this wire would need to go to positive. This part of the jack is negative on the outside. So I'll just solder that on real quick. It's not the best looking, but it's only temporary, so I can determine how this is going to behave when I connect power to it, and also put a battery in it and see what it does. Alright, we got the jack on there. The polarity is correct. I'm just making sure because I only get one chance to get it right. And now I'm going to take it over to the other workbench, or battery shelf, or whatever you want to call it. And I'm going to attempt plugging a solar panel straight in. But before I do that, I'm going to choose a battery and use that as my test subject to see what happens. In order to do some testing, I want batteries that are pretty empty. Most of my power tool batteries sit around about half full or nearly full. These two were used for weed whacking today, so I know they're pretty much used up. So I'm going to go ahead and measure them to see what they're at before I start using them as a test subject. So put it on 20 volts. Measure the first one. 16.5 volts. So yeah, pretty well discharged. The other one, a little bit less. So this one's a little bit less full than this one. I believe this one is pretty much flat dead. So I'm going to take these over to the other workbench, and I'm going to do some testing and experimenting to see how the charger acts if I just hook a solar panel straight up. If you haven't seen some of my other videos, I actually have two workbenches in here. I'm inside of what I call my cabin, which is, it's actually a wooden building or structure built inside of a metal building, which I call a solar workshop. Really, this is the workshop part, because I spend most of my time in here if I have any time to work. And you'll see here, this is a smaller workbench which I built. It's actually going to be a battery shelf, but it's nice to have an extra workbench. It's not my main workbench, but I do come here a lot, and I have a lot of junk piled up. So this is where I'm going to do the testing, and it's also where the solar panels are connected, so it's more convenient. This is what I call the solar power equipment board. I have several of these throughout the property. This one I built just for the workshop here. And I have two 100 watt solar panels that are flat mounted on the outside of the wall on the metal building. Those are used for experiments, charging batteries, and so forth. And the connection comes right in to the power board, and that's why I'm going to do the experiment here. I have been doing quite a bit of work in this area, but I have not done much on the solar power equipment board. There might be one or two additional videos about that in the future. Right now I'm having to focus on other things. I have a single 100 watt solar panel connected to this meter here, and it connects to this box here, and I have a 2.1 millimeter cord which I can use to power up any experiment I need to, and then I can see what happens on that meter right there. I'm simply going to take the solar panel and put it right into this charger with no regulation whatsoever and see what happens. Alright, let's plug it in. It's powered on. So I'm getting 17.98 volts in to the charger. Of course, that isn't ever going to charge a power tool battery all the way, but I'm curious what will happen if I just go ahead and put a battery in there that's fairly low voltage and just see what happens. So let's go ahead and just put the charger on top of the battery. Here's the battery. And it's blinking. It's actually trying to charge it. 20 watts, but the voltage is jumping around a little bit. The wattage is jumping around a little bit. So actually, it's charging. It's actually charging straight off of solar. It was not possible to see the meter, so I'm going to try it again. It's jumping around a little bit. Now keep in mind, this is just a solar panel shoved straight into a Ryobi battery charger, and it does appear to work. And this is actually quite interesting to me because I don't necessarily fully charge my power tool batteries. And one of the things I often do is I put a battery on the charger intending to take it off before it's full. And then I forget about it and I come back and the charger has already fully charged the battery. So I like to keep a storage charge in my batteries. That means partial state of charge. This actually would be a solution for me because I can just have the option of plugging a solar panel straight in. The experiment has been running a few minutes, and as I expected, the current is tapering off. It's now down to 0.69 amps and about 11 or 12 watts. And that's because the battery needs a much higher voltage than the solar panel can provide. 17.6 volts on this solar panel is nothing. It really should be down around 15 volts. This particular solar panel has a very low maximum power point voltage. 15 volts would not be unexpected, maybe 15.5 volts. As you can see, the battery is around 17.6 volts. So really, it's never going to get fully charged, but it's interesting to have the option to trickle charge and not fully charge a power tool battery without having to monitor it or do anything. It'll be an actual Ryobi charger, which has all the necessary circuitry and protections in place. Of course, this voids the warranty, but what do I care? Back over to the other workbench. It's encouraging that the Ryobi charger did not care that a solar panel was plugged straight into it. It did not care that the voltage was less than the normal amount, it just kept working. I actually like that very much. Not that Ryobi ever intended or authorized a solar panel to be attached directly to their charger, but it was a dud charger on eBay anyway, and it was going to be thrown away. So I'm certainly making use of junk.